Our next main topic we're going to talk about is called electric flux. The word flux means flow. So electric flux fundamentally is the flow of electric field lines through some sort of surface area. So I want you to imagine for a second that it's raining. We have this nice steady flow of rain just coming down to the ground. And I have a big rain bucket. So let's say I just have a big bucket out there. Not all of those, so the lines representing the raindrops falling down. And yes, I'm making it a bit ideal that they're all just coming straight down. Not all of the lines, though, pass through the surface area representing the top of the bucket. Meaning not all of this rain would get into the bucket to then be stored up for later. So when we talk about flux or flow, only some of these lines would be passing actually into the bucket. That would be a water flux of sorts. If I was using a smaller bucket, say one that was smaller like this, that would have even fewer lines passing through this open top, that surface area. And so what we mean by electric flux is, well, if I have electric field lines from some source, it doesn't matter ultimately what the source is right now, that's something creating an electric field, and I have something like paper, something that has a rectangular surface. This surface area of the paper, in terms of the picture I've drawn, has 3 lines passing through it. This fourth one on the right is not passing through. And I mean specifically not passing through that surface area of the paper. This left-hand one is not passing through either. And so those would not be part of what we call electric flux. The electric flux is determined solely by the field lines that can pass through that surface area. Now, there is another factor that can come into play. For example, if I take this paper and I rotate it, let me see if I can draw this okay. Okay, so start that part again. I take my rectangle, my paper, and I rotate it. So now it's at this steep angle. Its surface area hasn't changed, but now there are fewer lines passing through. And that's just simply because of the orientation of this paper. So the electric flux does depend upon the strength of the electric field. If you remember the way we draw our electric field lines, how the spacing between them is representative of how strong the electric field is. Here, I tried to draw my lines representing the electric field uniformly spaced so that it would be a uniform electric field. But if I had drawn, say, twice as many lines, that would have represented a much stronger field. So the strength of the field determines how many lines we draw here. And then the orientation of whatever surface we're talking about, whatever surface area that we're talking about the field lines passing through. For a uniform electric field, meaning it has the same value regardless of which line we're talking about passing through the surface, the electric flux, it is represented by the symbol phi. The electric flux can be written as the electric field vector dotted with the area vector. Now, the area vector has a magnitude and a direction. The magnitude is whatever we would use, for example, a rectangle. We would take the length times width to find the magnitude of the area. The direction of the area vector is always normal to the surface. If you remember, normal means perpendicular to the surface. So if I draw my little rectangle down here a little bit farther, its area vector is going to point either straight up or straight down. When we have just this two-dimensional surface, there's no way to really distinguish between the two. So typically, in a two-dimensional surface, we would choose the direction that matches the electric field we're talking about. But ultimately, there's no way to determine which one of them's not correct, is what I'm trying to say. But as long as we're talking about the normal vector specifically, this area vector must make a right angle with, the surface area. So in this situation where we have an electric field that is uniform, we can calculate this electric flux by taking the electric field vector and dotting it. This is the dot product, dotting it with this area vector. You might remember we can generically write a dot product equation as the magnitude of the two vectors times the cosine of the angle specifically between the two vectors. So the angle between the electric field vector and the area vector. If you remember, the dot product gives us a scalar answer. It's not a vector. It does not have a direction associated with it. It's just a number. It also multiplies the parallel components of our two vectors. So if I come back to my picture and think about this rectangle being at an angle, here is our area vector. That's the direction that's normal to the surface. Or we could draw it coming down this way, normal to the surface. Either way, the electric field that we were just working with is pointing straight down. So the angle I would care about in terms of calculating would be this theta specifically. So the angle between the normal vector and the electric field. So when we say the electric flux is EA cosine theta, we specifically mean this theta. We have to be intentional and thoughtful about making sure we're using the correct angle in the calculations. But this hopefully helps make sense. Even though we have all these electric field lines passing down, by rotating this piece of paper, this rectangle, we now only have the component of, we can think of it either as the component of the area so component of the area vector that is in the y direction with the electric field. Any x components would not be passing through. We can also think of it as the electric field broken down into a component that lies along the area vector and a component that lies perpendicular to it. In that case, that would still be the E cosine theta. So we could say E cosine theta times A. This would be the component of the electric field in the direction of the area vector. Either way, it means the same thing. We're just finding the components of the vectors that lie along the same line. And that's because it's only these components that are along the same line that would actually pass through the surface. If I took my piece of paper and ended up orienting it vertically, in the region we had this electric field, there would be no flux. No lines would be passing through that surface. Going back to the example with it raining, the rain coming down, holding your bucket sideways, you're not going to get any rain in the bucket. This area vector is perpendicular to the electric field that's coming straight down, or the raindrops that are coming straight down. And so no raindrops would be passing into the bucket to be stored. So flux is just this measurement of a flow through a surface area. I'm going to rewrite this equation down here. So for a uniform electric field, the electric flux can be calculated by taking the electric field vector and dotting it with the area vector. Which another way of solving that is taking the magnitude of the two vectors and multiplying those together and multiplying those by the cosine of the angle between those two vectors. You might recall another way of doing the dot product is to have the vectors written in terms of their XYZ components. If that is the case, then we would just multiply those individual components together and then add it all up. Now keep in mind, we have a scalar answer here. It is not a vector. There's no in the x direction, y direction, z direction anymore. If the electric field is not uniform, we end up needing to integrate the value of the electric field over the surface area, which we could also write that as E cosine theta dA, but we would need to write theta and the dimensions of our rectangle, for example. Our area would be little pieces of area, so a little dx times a dy. And we end up having a double integral because we have to integrate over x and y, both. So both over this way and this way. if we have a situation where the electric field is uniform in one direction but not the other. For example, if it was uniform along the x-axis but not the y-axis, we could call this dA x to represent the entire length along the x-axis, and then a dy to represent adding up these little segments as we go across the area. For now, any integral you will see will give you a function describing the electric field. And then the area, if the function depends only, so if the function for E depends only on y, then dA would be this x dy. If we were given a function that described the electric field changing with x, so if the function for the electric field depends only on x, then dA would be y dx. The y would represent the length along the y-axis, and then dx would represent these little tiny lengths. So we would be breaking it into rectangles to add up. So we'll look at that later as well. A lot of our situations that we're going to talk about right now is for a uniform electric field. So for example, let's say we have a region of space where the electric field is, I'm just going to make up some numbers. So our electric field has an x component, a y component, and a z component. The x component being 100, the y component being 200, the z component being 300. So let's say we have a square that's, 15 centimeters on the side. I want to find the electric flux in a few different orientations of this square. So let's say first, so we're going to find the electric flux in each of these situations. So the first situation, let's say our square is parallel to the xy plane. So if we think about our coordinate system, our typical Cartesian coordinate system, x has been horizontal, positive to the right, y has been vertical, positive going towards the top of the page. Positive z direction in this situation would point out of the page or the screen, because it's perpendicular to both x and y, specifically in the order of x cross y, for those familiar with the cross product. I don't draw three-dimensionally very well, so I'm just at the moment drawing our square in the xy plane. So it's perfectly parallel to the xy plane. It's not telling us where specifically in the plane it's located, but that's okay, because this electric field given up here, looking at it, there's no x, y, or z variables. So this is a uniform electric field. So to calculate the flux, we're going to take E dotted with the area vector. Now the area vector, remember, has a magnitude, which is just the area of this shape, and it has a direction. So the magnitude of this, since we have a square, is just going to be the two sides, the length of the both sides, 0.15 meters squared. So I'm essentially saying that both sides has a length L. Since it's a square, we end up with L times L, or L squared. So this is the magnitude of the area vector. The direction is always normal to the surface, meaning it's perpendicular to the surface. Since this square is in the xy plane, the z direction is the direction that is normal to the surface. So our area vector in this case would be 0.15 meters, all of that squared, in the k-hat direction, the z direction. So when we go to do the dot product, the 100i plus 200j plus 300k dotted with this 0.15 meters squared k, well, the only component of the electric field that is actually passing through this square is the z component. And we may very well recognize that up front and just say the z component times the area. Because any x component of electric field can't pass through. The y component cannot pass through this square over here. Only the z component could actually physically pass through that square. And so that's also the nature of the dot product, is to take the k-hat, dotted with k-hat. So we have the 300 newtons per coulomb for the electric field. We have the 0.15 meters, that quantity squared, for the area. And keep in mind, k dotted with k is just the number 1. We don't get a direction on our answer. So I'm getting 6.75, which I haven't really been careful with looking at units. But if we go off of the 15 centimeters on a side and assume these 100, 200, and 300 are accurate to 3 sig figs, we would end up with 6.8. Our units, well, we just have to look at the units on these numbers we just plugged in. The units are newtons times meters squared per coulomb. That would be the electric flux through this square. That's not going to be the electric flux if we change the orientation of the square. And that's what we'll look at next. So the second situation, let's have our square parallel to the xz plane. So I'll make an attempt of kind of drawing three-dimensionally. X, Y, Z. Our square is now down in this plane. So ultimately, it still has dimensions of 0.15 meters on a side. So the magnitude of the area has not changed, but the direction of the area vector has changed. It's always perpendicular to the surface, but what's changed is what direction that is in. It's no longer in the z direction. So the area vector magnitude still 0.15 meters squared, quantity meters squared, but now it points in the y direction, because that's the direction that is perpendicular to the surface. So if we think again about the dot product, we're still taking E and dotting it with A. But if we think about the electric field, the X component of the electric field will not pass through that square. The Z component will not pass through that square. It's only the Y component that can pass through that square now. And that's what we get when we dot the electric field with this area vector that points in the Y direction. J dotted with J is what will give us the 1, which leaves us with taking the Y component of the electric field and multiplying it by this area. So this time the flux is smaller. It is smaller because this Y component of the electric field is smaller than the Z component was when we looked at the previous situation. So with the electric flux, we need to know the electric field. We need to know how the area, the surface area we're talking about, is oriented relative to the direction of the electric field so that we can calculate the flux. So I'll go through some examples and a couple concept questions, and then we're going to build on this and talk about the electric flux through a closed surface. So what we've talked about so far is considered an open surface. It's just a two-dimensional. It's a square, it's a rectangle, it's a circle, it's a triangle. A closed surface is three-dimensional. It's going to be a sphere or a cube, a prism, any type of shape that has both an inside and an outside. So the surface is completely closed off and shut to the outside. The general idea is still the same. We're still going to look at electric field passing or flowing through the area, but we'll have a couple of other things to add to this as we continue.